This video is about refrigerants. What is a refrigerant? Refrigerants are in your air conditioner and your refrigerator. The refrigerant is the gas inside the tubes of your air conditioner or refrigerator. Why should I watch this video? Refrigerants are one of the greatest inventions of the 20th century. Refrigerants are becoming a dangerous safety hazard. Yes, refrigerants are one of the greatest inventions of the 20th century. However, refrigerants face modern problems, environment problems, and safety problems. Let's start by imagining a world without refrigeration or air conditioning, like the world that existed before the 1930s. Most of the world's tropical or desert areas were very sparsely inhabited. This photo shows a familiar location in the southern United States. Can you guess where it is and when? This is Miami Beach in 1914. Obviously, your first question is, where's the Fontainebleau Hotel? Where's any hotel? None of the big modern buildings along Miami Beach could be possible without the invention of safe, efficient, reliable air conditioning and refrigeration. Here are some early pioneers in the technology of cooling things by the compression and expansion of a gas. In 1856, Australian inventor James Harrison patented a machine for making ice through compression of ether vapor. A dozen of his machines were operating in 1861. In 1877, the French ship Le Frigorifique, equipped with a refrigeration plant designed by Charles Tellier, delivered a cargo of frozen meat from Rouen to Buenos Aires. It was now possible to ship meat from the massive herds of distant agricultural nations to markets in Europe. If you want to learn the engineering specifics of the refrigerant cycle, go to the 5 slides at the end of this presentation. In 1902, Willis Carrier designed the first modern air conditioning system to solve a production problem at the Sackett and Willems printing plant in Brooklyn, New York. Carrier is known as the father of air conditioning. The first public display of air conditioning of a building was the Missouri State Building at the St. Louis World's Fair in 1904. Here is an early domestic refrigerator in 1914. The first domestic refrigerators were too expensive to be purchased by the average family. In 1916, the average USA worker would have to work over 3,000 additional hours to be able to buy a refrigerator. However, by 1929, refrigerators were beginning to appear in USA households. Industry-wide sales increased to 730,000 in 1929. Despite the early technical successes, refrigeration and air conditioning remained a risky technology. The early refrigeration machines used refrigerant gases that were toxic, explosive, corrosive, or all three. For example, ammonia, methyl chloride, dimethyl ether, sulfur dioxide. refrigeration machines in air conditioning plants required constant supervision by highly trained operators. Although refrigerators were available, the tubes of existing refrigeration equipment contained dangerous gases. The death rate from refrigerant gas poisoning was alarming. In Chicago, at least 15 people died from leaks of toxic refrigerant gas in the first half of 1929. It is no surprise that most households in the northern USA had ice boxes instead of refrigerators to cool their perishable food. In the northern states, the daily visit from the iceman was an institution, while in the southern states, ice was not available. In the southern states, in the summer, wealthy people left for the northern border states or Canada, while poor people suffered through the stifling heat. In 1929, General Motors was the owner of the Frigidaire Corporation, the manufacturer of many of the refrigerators that contain toxic refrigerant gases. Charles Kettering, the vice president of General Motors Research Corporation, realized that refrigeration and air conditioning were being held back by serious refrigerant safety problems. Kettering assembled a talented team of chemists and engineers led by Thomas Midgley, and asked them to develop a safe refrigerant gas that would meet the requirements of a refrigerator or air conditioning system and was non-toxic, non-flammable, and non-corrosive. Within a year, Midgley's team had synthesized and proved the value of difluoromethane, CCl2F2, as the ideal refrigerant. The new CFC refrigerant possessed all the required safety features and performed well in the refrigeration cycle. The CCl2F2 molecule is based on methane, CH4, the primary component of natural gas. However, methane's 4 hydrogen atoms are replaced by 2 chlorine atoms and 2 fluorine atoms. The CCl2F2 molecule is sturdy and robust, highly resistant to chemical attack. Replacing hydrogen with chlorine and fluorine in the molecular structure of methane eliminates flammability. In 1930, Midgley presented his new safe refrigerant at a meeting of the American Chemical Society by lighting a candle, inhaling a lungful of the new refrigerant gas, and then gently blowing out the candle flame. In 1931, a U.S. patent was awarded to the Midgley team for the invention of a range of CFC refrigerants, including CCl2F2 refrigerant 12 and others. The fact that CFCs do not corrode metals enabled manufacturers to build air conditioners and refrigerators that required no maintenance. In these two photos, an open compressor in an industrial ammonia refrigeration system is compared to a hermetic compressor in a CFC refrigeration system. The open ammonia compressor is driven by an electric motor that is not exposed to the corrosive ammonia vapor. The motor transmits power to the compressor by a rotating shaft that penetrates the compressor enclosure. A rotating shaft seal prevents the ammonia vapor from escaping from the compressor. However, the shaft seal is not perfect. Ammonia is slowly leaking from the shaft into the air. We can probably smell the leaking ammonia. This ammonia-based refrigeration system requires annual maintenance to replenish the leaked ammonia. In the hermetic CFC compressor, the electric motor, drive shaft, and compressor are completely enclosed in a sealed container. The CFC refrigerant does not corrode the copper wiring of the motor, which is cooled by a constant flow of cool refrigerant from the evaporator. Only the wires and the refrigerant tubes penetrate the enclosure. This CFC compressor requires minimal maintenance. After the invention of CFC refrigerants and hermetic enclosures, air conditioning and refrigeration became household appliances that required no expert supervision. A consumer could buy a refrigerator and a window air conditioner in an appliance store and install them without special skills. The refrigerator could preserve fresh food for weeks. The air conditioner could maintain a comfortable temperature in several rooms in the hottest climate. The invention of safe refrigerants was a disruptive technology, like the invention of the automobile or the invention of the radio. Safe refrigerants changed the history of the world. Large desert and subtropical areas of the United States, for example Arizona, Texas, Florida, previously sparsely inhabited, suddenly became prime real estate. The population center of the United States shifted south and west. Safe, reliable air conditioning changed the political, cultural, and economic landscape of the United States. Major hot weather cities like San Diego, Houston, Atlanta, and Miami began to rival the economic, cultural, and political power of New York City, Chicago, Boston, and Philadelphia. The U.S. Energy Information Agency found in 2009 that 87% of U.S. households had air conditioning. The development of safe, reliable, mobile refrigeration changed the diets of millions of people who now had access to unspoiled fresh food produced in faraway agricultural lands. Pharmaceutical makers could now ship vaccines to other countries in refrigerated containers. The fresh available vaccines contributed to major improvements in the fight against infectious diseases. Just imagine where we would be in the current COVID-19 pandemic if refrigeration were not available to transport and store vaccines. Even now, this expansion of air conditioning and refrigeration is sweeping across the globe. Air conditioning and refrigeration are enabling the growth of large populations and powerful economies in hot countries in the Third World. By 2050, around two-thirds of the world's households could have an air conditioner. China, India, and Indonesia will together account for half of the total number. That's a quote from the International Energy Agency. To add to the rush toward refrigerant use, some non-government organizations are now promoting the use of heat pumps instead of fossil fuel combustion to heat our buildings. A heat pump uses a refrigerant cycle to transfer heat from a source to a load. By 1969, more than half of all new automobiles sold in the United States were equipped with air conditioning, which is now a standard feature in new automobiles. The honeymoon ends. It was too good to last. The fairy tale of CFC refrigerants suddenly soured in 1974 when chemistry professor Sherwood Rowland and postdoctoral fellow Mario Molina at the University of California, Irvine, showed that CFCs leaking from refrigeration and other sources were destroying the Earth's ozone layer. Measurements showed that CFCs were accumulating in the ozone layer at the outer edge of Earth's atmosphere. Other measurements showed that more and more dangerous ultraviolet radiation from the sun was reaching the Earth's surface, particularly at the holes in the ozone layer at the north and south poles. Ironically, we could speculate that Rowland and Molina's accomplishments at the University of California may never have happened if safe refrigerants enabling economic and scientific growth in California had never been invented. We should mention that most of the CFCs escaping into the atmosphere are not from refrigeration or air conditioning. Most of the CFCs in the atmosphere are aerosol propellants, cleaning solvents, or blowing agents for plastic foam. Rowland and Molina showed that when CFCs escape in the lower atmosphere, the sturdy, robust CFC molecules are not destroyed or captured by oxidation or natural atmospheric processes. The leaked CFC molecules eventually arrive in the Earth's ozone layer, where the CFC molecules are split apart by high-energy ultraviolet radiation from the sun. The broken up CFC molecules release chlorine-free radicals. A chlorine-free radical is an individual atom of chlorine not bonded to another atom. Each extremely reactive chlorine-free radical attacks molecules of ozone, O3, over and over, destroying the ozone molecules that protect the Earth's biosphere from damaging ultraviolet radiation from the sun. The growing concern about depletion of the ozone layer by CFCs and by other ozone-depleting substances led to the Montreal Protocol on substances that deplete the ozone layer, signed by all 197 UN member states in 1987. Following the signing of the Montreal Protocol, the United States EPA issued a final rule to phase out completely the production and consumption of CFCs in the USA by January 1, 2001, later amended to December 31, 1995. The Montreal Protocol is often cited as a huge international environmental success, currently repairing the Earth's damaged ozone layer. The air conditioning and refrigeration industry complied with the new 1987 rules by switching to less ozone-depleting refrigerants. Midgley's infamous CFC refrigerants were replaced by HFC refrigerants, for example R134A, a non-flammable, non-toxic, non-corrosive refrigerant with acceptable refrigerant cycle performance and an ozone-depleting potential of 0. And now things start to heat up. The timing could not have been worse. Just as global warming was making the Earth more and more unlivable, just as the adoption of air conditioning was sweeping across the developing world, we discovered that refrigerants themselves are contributing to global warming and climate change. The sturdy, robust CFC and HFC refrigerant molecules, leaking from refrigeration and air conditioning systems and other sources, survive their journey through the lower atmosphere and eventually arrive at the greenhouse layer at the outer edge of the atmosphere, where they block some of the Earth's infrared emissions into space. The result, global warming. Although the total mass of these refrigerants is much less than the total mass of carbon dioxide, the principal greenhouse gas at the greenhouse layer, refrigerants are powerful absorbers of infrared radiation, and they are growing rapidly in use. Here are the global warming potentials, GWP, of some refrigerants compared to carbon dioxide, CO2, which is assigned a GWP of 1. Unfortunately, R134A, a non-toxic, non-flammable, non-ozone depleting hydrofluorocarbon, HFC, refrigerant, is a powerful greenhouse gas. With a GWP of 1,300, 1 kilogram of R134A causes as much global warming as 1,300 kilograms of carbon dioxide. In 2016, at a United Nations conference in Kigali, Rwanda, the international community agreed to reduce the consumption and production of HFCs. Currently, 93 countries and the European Union have ratified the Kigali Amendment to the Montreal Protocol. The Kigali Amendment will reduce the projected production and consumption of hydrofluorocarbons, HFCs, by more than 80% over the next 30 years. If fully supported, the amendment will avoid up to 0.4 degrees Celsius of global warming by the end of this century. an ironic twist. Before the Kigali conference, the Rwandan hosts installed air conditioning in the meeting hall. The chemical industry is developing new refrigerants to replace CFCs and HFCs. The most promising candidates are hydrofluoroolefins, HFOs, which have low ozone depletion and global warming numbers. The first of these HFOs is R1234YF, which is now being installed in the air conditioning systems of new cars. Some appliance manufacturers are now filling new refrigerators with hydrocarbon refrigerants. That's right, hydrocarbons, like propane, isobutane, and R12A, a mixture of propane and isobutane. The HFO, known as R1234YF, has good refrigerant properties and is non-ozone depleting and is not a greenhouse gas. The website Vehicle Service Pros reported in 2018 that about 50% of new cars were being equipped with R1234YF in their air conditioning systems. However, R1234YF is an extremely flammable gas. During combustion, R1234YF produces toxic corrosive gases. One major motor vehicle manufacturer, Daimler AG, the manufacturer of Mercedes-Benz cars, refuses to install R1234YF. After testing the new refrigerant for flammability and toxicity, Daimler notified the authorities in September 2012 that it wanted to recall all 1,300 Mercedes cars worldwide that had already used the new refrigerant. Daimler's concerns were confirmed by a 2014 study released by LMU University Munich. The International Labour Organization describes R1234YF as an extremely flammable gas. Gas-air mixtures are explosive. Here are the URLs of some websites which describe the widespread use of R1234YF in motor vehicle air conditioning and its hazards. In 2015, the United States EPA announced that some hydrocarbon refrigerants would be allowed in domestic and commercial refrigeration equipment in the USA. This new rule permits the use of propane and isobutane in household refrigerators, freezers, vending machines, and some room air conditioners. The maximum permitted charge per appliance is 150 grams of refrigerant. In some countries, R12A recharge cylinders for vehicle air conditioning are for sale in retail stores. R12A is a mixture of isobutane and propane. Hydrocarbon gases have some desirable properties as refrigerants, but hydrocarbons are explosive, flammable gases. Millions of refrigerator freezers with propane refrigerant are now in use around the world. In each of these refrigerators, the explosive propane refrigerant is contained within the hermetic enclosure. However, any puncture of the refrigerant tubing will allow the explosive propane to leak into the room. This reversion to hydrocarbon refrigerants is a disaster waiting to happen. In fact, a disaster has already happened. On October 23, 2006, in Panama City, 42 passengers aboard City Bus 8B06 noticed a strange odor from the air conditioning system. Suddenly, R12A refrigerant gas leaking from the air conditioner ignited into a blazing inferno that filled the entire passenger compartment. 18 passengers died, including 5 children. 24 were badly burned but survived, some requiring multiple surgeries. In other countries, media reports of fires from leaked refrigerant mention the danger from hydrocarbon refrigerants. We face an uncertain future as the growing demand for refrigeration and air conditioning in a warming world collides with the environmental and safety problems of refrigerants. Where do we go from here? And now some engineering. This is a description of the refrigerant cycle in a window air conditioner. You can follow the process in the next 3 slides. You can print this slide from the YouTube video and use it to explain the next 3 slides, or just listen to the narration. How does a refrigerant gas provide cooling? What happens to the refrigerant gas when it goes through the refrigerant cycle? Here is a description of the refrigerant cycle in a window air conditioner. You can follow the process for a typical refrigerant gas, R134A, in these 3 slides. Let's start at the entrance to the compressor. 1. The refrigerant gas at low pressure and a cool temperature is sucked into the compressor, where it is compressed to a high pressure. 2. This compression makes the gas very hot. The hot gas flows to an outdoor coil of tubes known as the condenser, where it gives its heat to the outdoor air. The hot refrigerant cools to a warm temperature and condenses from a gas to a liquid, still at high pressure. This warm, high-pressure liquid passes through an expansion valve or capillary, where it suddenly expands into a low pressure. This suddenly vaporizing refrigerant becomes very cold as it changes back to a gas. 4. This very cold mixture of cold vapor and vaporizing liquid passes through an indoor coil known as the evaporator, where the refrigerant gives its cold to the indoor air. The refrigerant emerges from the evaporator as a cool, low-pressure gas ready to repeat the cycle. This is a simplified line drawing of the same cycle as the previous slide, this time showing the components and refrigerant tubes. Viewers who are familiar with the science of thermodynamics can follow the path of the refrigerant through the same cycle using the third diagram, pressure versus enthalpy, also known as a Mollier diagram. Each refrigerant gas, and there are dozens of different refrigerants, has a unique Mollier diagram which can be used to choose a suitable refrigerant for a given situation. And now some chemistry. Here is a historical summary of the development of refrigerants. You can print this slide from the YouTube video or just stop the videos to examine the slide.